Elimination reaction are important class of organic reaction. These reactions usually proceed through different mechanisms such as E1, E2, E1CB mechanism, pyrolytic elimination, and the last category of such elimination reaction proceeds through an alpha elimination reaction. So far we have studied different mechanisms with respect to elimination reactions. These mechanism includes E1, E2, E1CB, pyrolytic elimination, and one last category of such reaction is known as alpha elimination reaction, or we call it 1-1 elimination. Usually we talked about unimolecular elimination and bimolecular elimination reaction. Both are an example of beta elimination. Or we call them 1-2 elimination reaction. Today we are going to talk about an alpha elimination reaction rather than beta elimination reaction, which we have studied earlier. This is beta elimination. So let's focus on alpha elimination. By considering an example which is the most common, this is chloroform, which can simply be written as CHCl3. So when it is treated with a strong base such as sodium hydroxide, we get a species plus water and a halogen atom. Here the species is known as dichlorocarbene. Usually carbene are interesting reactive intermediate. We will focus briefly on its chemistry. For example, species like A and B can be two atoms that can be same or different, such as two hydrogen, one hydrogen and one halogen, such as bromine, or two halogens. So all such species are electron deficient in character. They are strongly electrophilic because they represent a deficit of for 2 electrons, because 2 electrons are deficit from octet completion. Here in these carbenes we have only 6 electrons in the valence shell of carbon atom. So for stability purpose it requires 2 additional electrons to get a stabilized form. So all these carbene are electron deficient and they act as electrophilic reagent. They are electrophilic because they are electron deficient in character, and they react with a nucleophile. Structurally, as far as their geometry is concerned, usually carbene are sp2 hybridized. We have 2 electrons in one of the sp2 hybridized orbital, and we also have one unhybridized p orbital that is perpendicular to the trigonal planar. So this is unhybridized. Let me clear it. This is unhybridized. P orbital. So as a whole, carbenes are sp2 hybridized species in which the lone pair of electrons reside in one of the sp2 hybridized orbital. With respect to unhybridized p orbital, it acts as a electrophile because the p orbital represent a deficiency of electrons, so therefore it reacts with electron or negative charged species. So on the basis of these unhybridized p orbital, the carbene acts as an electrophile, and as far as carbene also has a lone pair, a 2 pair of electrons, due to which it also acts as a nucleophile. So carbene can act as both the electrophile and a nucleophile. Nucleophile, electrophile due to unhybridized p orbital, where nucleophile due to presence of a lone pair in the structure of a carbene. So this simple chemistry with respect to carbene. Let's return back to the reaction. Here we have a typical reaction in which a chloroform, especially any haloform, can act as a good substrate for alpha elimination reaction. So in alpha elimination reaction, 2 group, especially both the leaving group and the hydrogen replaced from the same carbon atom. This is alpha carbon atom, no, 1 hydrogen atom and 1 chlorine atom. So both are replaced from the same alpha carbon atom, so that's why we call it an alpha elimination, or we also call it 1-1 elimination reaction, unlike 1-2 elimination or beta elimination reaction. Basically, the reaction proceeds through 2 steps. Step number first is fast, which involve the abstraction of hydrogen. Let we have bromoform, and we get a carbanion, like this is the carbanion that rearrange for expelling the leaving group from the molecule in the second step. So in second step, Let me write again. The leaving group leaves a molecule, and we get a bromocarbene. This is known as bromocarbene, and by this way we get the carbene like a species. So the reaction is two-step. Step number first. Step number first is fast, and step number second is a slow step, and in fact it is rate determining step where only a carbon ion is involved, so therefore we call it a unimolecular elimination reaction, or the kinetic of this reaction is unimolecular in character. Carbon ion, so it is unimolecular. If we focus on the mechanism is closely related to E1CB mechanism. In E1CB mechanism, we also noted two steps. The first step was fast, which involved the abstraction of proton by the base, especially a strong base. Usually in alpha elimination reaction also a strong base is required. Here a strong base is required. In the first step of E1CB mechanism, we noted that a carbon ion formed much like the alpha elimination. Here in the first step also we get a carbon ion. In second step of E1CB mechanism, we noted that a leaving group leave from the molecule along with the corresponding adjustment of the double bond. Here there is no formation of the double bond, but the leaving group leave from the molecule, here in this case a bromine atom, and this second step is slow and rate determining in character. So in E1CB mechanism a double bonded compound is formed, and alpha hydrogen is removed from alpha carbon, and the leaving group leave from a beta carbon atom, unlike alpha elimination in which both the hydrogen and the halogen atom are removed from the same carbon atom. So that's why we call it an alpha elimination or 1-1 elimination reaction. Consider an example. We have a species like and it reacts with a bromoform. This is a bromoform in the presence of some strong base, and we get a product. Like this. So in order to predict how the product is formed, we need to focus on the mechanism, how a carbene is generated. Similarly, we could have another example as well, which is cyclohexene, and it reacts with a chloroform in the presence of base. We get an interesting bicyclic a compound in which cyclopropane ring has formed, to which two chlorine group are linked. So in order to understand both the example number first and number two, we usually form carbene in the first instance, and that carbene then ultimately add to the double bond. Consider, let me take base such as OH. It when react with a bromoform, a carbene like this is formed CBr2, which is diabromocarbene. Let me clarify it a bit. CBr2, this is diabromocarbene, and this is electrophilic in character. When it is treated with a double bond, especially such as compound like this, CBr2, it add like this and we get a cyclopropane system. So in both examples, the carbene is formed as a reactive intermediate and then react with a double bond. Usually carbene are unstable, they cannot be purified. They are unstable, they cannot be purified, so they are usually made during the course of a chemical reaction when they are needed. For example, if we try to isolate them, they will automatically react with it. For example, if we have a methylene carbene and another methylene carbene, so they will automatically react very fastly and we will get alkene, which reflects that carbene are highly unstable species, so they cannot be isolated. Usually they are generated where they are needed, as in about two examples where carbene have two different carbenes have generated for reacting with a double bond. Usually for alpha elimination, a strong base is needed. A strong base is required for affecting alpha elimination reaction. Just for example, we can have different compounds such as dichloroalkane. Even for example, instead of haloform, we can have an example like this. So if we have this is known as vicinal dihalide. For example, if we have two halogen molecule linked to the same carbon atom, so such molecule are known as geminal. Geminal dihalide. If they are linked to two different carbon atoms, we call them vicinal. Halides. So in case of vicinal dihalide, right over here, when a strong base such as LDA, which is known as lithium isopropyl lithium diisopropyl amide, if this base is used, usually it can cause an alpha elimination reaction even in vicinal dye or a geminal dihalide. For example, here we have a geminal dihalide. So if it is treated with LDA, we can get a species like this species, which is known as a chlorocarbene. Even if the capability of base is further intensified, especially if we take more strong base, such as the combination of tertiary butyl lithium and tertiary butoxide, which acts as a very strong base. This combination acts as a very strong base, and it abstracts protons even from allylic and benzylic position, or even it can take a proton from benzene ring as well. This is a very strong base, which is known as closure base. So in, for example, if we take a simple halide, especially primary in character, this is a primary alkyl halide, and if we take the above base, so we get the desired chlorocarbene. Another interesting example with respect to alpha elimination reaction is Simmon-Smith reaction. In which diiodomethane is reacted with zinc copper couple for giving a species like this, which is organozinc compound or an important organometallic compound. This is organometallic compound, which is known as Simmon-Smith reagent. Simmon-Smith reagent, that is an important organozinc compound. Usually when organic compound is bonded with a metal, then such type of compound are known as organometallic compound. Usually Grignard reagent is an important example of organometallic reagent. Besides, we can have organocopper or organolithium compound. So here in this reaction we get a species like Simmon-Smith reagent, which is known as a carbenide. This Simmon-Smith reagent is known as carbenoid because it has the capacity to generate a carbene-like species. For example, let me sketch it again. So zinc usually live by giving its lone pair of electron. When the zinc or the metal is removed, then a negative charge is formed. This is CH2. Let me clarify it a bit. Here I have CH2 group. When the zinc leave, it usually donates its bonded pair of electron to the carbon atom. As a result, we get a carbene, and in the next step the iodide ion leaves from the molecule and we get methylene carbene, and this methylene carbene then ultimately add to the double bond. Usually a Simmon-Smith reaction, a cyclopropane are made. In other words, we can say that the Simmon-Smith reaction is used for synthesizing a cyclopropane alkane. So this removal of zinc metal and iodide in two steps can also occur in a single step as well, like this, and we get a methylene carbene which adds to any alkane compound such as, and we get a cyclopropane system. So usually Simmon-Smith reaction is used for synthesis of cyclopropane. So let me revise important concepts again by moving to the first slide. Usually elimination reaction proceeds through different mechanisms. We can have E1, we can have E2 elimination, we can have E1CV mechanism. Elimination reaction also proceeds through pyrolytic mechanism, and in the end we have an alpha elimination, also known as 1,1 elimination reaction as well. So as far as alpha elimination is concerned, it is two-step mechanism. The first step involves the abstraction of protons from the substrate, which is haloform, and for giving a carbene, the first step is forced. The second step involves the loss of a halogen atom. It is slow and rate-determining in character. Its kinetic is unimolecular because it depends upon the rate of reaction, depends upon the concentration of a carbene. Indirectly, it also depends upon the concentration of base, because base is required for making the carbene, much like an E1CV mechanism. So in E1CV mechanism or an alpha elimination reaction, we get a carbene. Usually carbene are electron deficient species. They are electron deficient, which act as an electrophile. Its structure is sp2 hybridized in character. We have an unhybridized p orbital which lies about below the plane. This p hybridized orbital is vacant, due to which it acts as an electrophile, and also we have a pair of electrons in one of the sp2 hybridized orbital, which make the structure to act like a nucleophile. As far as these two examples are concerned, the reagent which I have used right over here usually generate a carbene in the first sense, and these carbene add to the double bond for giving a cyclopropane ring, which is halo substituted. Both examples reflect the same mechanism. Carbene are a highly unstable species. They cannot exist under ordinary temperature and pressure, because if we try to isolate them, they will automatically react for giving an alkene. Usually for catalyzing an alpha elimination reaction, a strong base is required, such as LDA or scalar base. Here we have noted. So even if LDA is used, we can affect an alpha elimination reaction from a geminal dihalide. Here we get a carbene, and if we use further strong base, then we can abstract or cause an alpha elimination reaction even from primary alkyl halide as well. So this is a very strong base. So this is all about an alpha elimination reaction. In the end, Simmon-Smith is an important reaction in which the double bond is converted into a cyclopropane system by using the reagents such as diiodomethane. This is diiodomethane, and it is reacted with zinc copper couple for giving an organo zinc reagent, which is known as Simmon-Smith reagent. and these Simmon-Smith reagents rearrange by giving a carbene that ultimately aid to the double bond for giving a cyclopropane system. So reagents like these are known as carbenides. Thank you for watching the video.